like to welcome all of you this evening on behalf of the Salina Astronomy Club and Kansas Wesleyan to our February Sky Watch. You are the brave, the hardy souls who have foraged out during the cold weather and gotten here for one reason or another. Just a word to students in my class, if you would please remember to sign. I've got a piece of paper up here, okay, so I have a record of attendance for tonight. I might be a little forgiving for people who haven't been able to make it and a little generous with extra credit for those of you who have, because the weather's been so nasty. But our topic tonight is just sort of open, interesting things going on in astronomy, and our original intention was to have several members of the Astronomy Club present things that they found interesting in recent events in astronomy, but one of our members was not able to be here because of a health reason. I was supposed to do one of those, and I have about a 5-minute talk, but because of the weather, I didn't really have a chance to do the amount of research that I needed to do. So it all falls upon Mr. Kassoff, who fortunately has prepared to discuss with us ICE. Is that ICE or ISIS?
ISIS.
ISIS, the cosmic dawn, and I'm sorry, I forget the other one.
The galactic structure.
The galactic structure. So a very large variety of topics, and if we have a little bit of time at the end, I want to share with you a little bit of what I consider to be exciting news about chemistry and astronomy, and you knew I was going to do that being a chemistry teacher, right? Okay, so with no further ado, Mr. Kassoff, the floor is yours.
Okay, hi. So I'm going to talk about several different topics, and I have extraterrestrial ice, so ET. They use it for different, can mean different things. It doesn't have to mean, you know, a movie about strange creatures. It can mean ice. And then I'll talk about the structure of the Milky Way, MW. A little bit about the Hubble images, and they had a grandmother test that it had to pass, which you'll find somewhat funny. And then why space science is less controversial than other subjects that people debate in this. I was reading about this organization, or actually it's a journal called Communicating Astronomy to the Public Journal, CAP. That's what that CAP stands for. And it's a really interesting thing that you have all of these scientists, you know, doing their research, and then they have the public, and they have to get across to the public why what they're doing is important. And so you have all these what they call PIOs, public information officers, that work for NASA, that work for the Jet Propulsion Laboratory, that work for these universities, and they write about how to explain this subject, what's going on in really astronomy. You know, they still use that term, but I think like 95% of all the work that's done is really astrophysics. The astronomy, in my mind, is almost like stamp collecting. That you look out in our galaxy and you see all these open clusters, and they're beautiful, they're lovely, and then you see the globular clusters, and so you can make lists of all of these deep space objects, which the amateur astronomers, they call them the fuzzies. And so there's lists in our galaxy of like 1,500 or so open clusters and like 160 globular clusters that are scattered around our galaxy. So they really want to try to get across why not only to catalog as a stamp collector would make lists of things, they want to be able to explain why these objects are interesting. And so that's what this CAP is about. So I had to do some testing. Science Olympiads every January, they compete middle school and high school kids. So I said, well, the topic this year was extraterrestrial ice. So the 7th, 8th, 9th graders, in theory, but no 9th graders wanted it. They're very ninth grade, and so they didn't want to really help the 7th and 8th graders. So I left out the math, and I read up on ice, and the most interesting thing that I read about was this business of one of the missions just a few years ago, and continuing, even now I think it continues, this Mars reconnaissance orbiter is observing the surface of Mars, and they use radar to penetrate and look down through the ice cap, and they look down. You think, well, radar is kind of neat if you're in the fog or something. You want to see, features if you're on a boat. You want to see what's around you. But their radar is a subsurface radar. It can actually penetrate, they say, like a half a kilometer into this ice cap. And so you actually see here an image where the colors are the topography at the bottom here. So I guess the white is the highest topography, and then as it falls down here, it turns to red, and then it goes on to this. Let me try this. It goes down to this yellow out here, and they have a scale here. They show 100 kilometers by 100 meters. So you'd say, oh, that's fine. But then if you think about that, what's that telling you? That's telling you that they expanded the scale on the y-axis, the elevation. They expanded it by a factor of 100. So if they had drawn this, like a piece of a square grid where every unit on the y-axis was the same as the x-axis, you would have, instead of 1,000 meters is 1 kilometer. So if I wanted that now to represent 100 kilometers instead of 1, I'd have to take all of these features and I have to shrink them down by a factor of 100. Okay, so it looks like a really powerful glacier, big range there, but in reality, it's a very thin feature. It's only 1/100th of the height that you see there, but they're expanding it so you can see all the detail. Okay, or if you didn't like it that way, you could leave it this way, but you could stretch it out left to right by a factor of 100, and you'd have just this thin, very thin layer of ice that's a kilometer thick. They say that all this is a mixture of water, ice, and dust, which is kind of interesting to know. We think of Mars as being this dry, desolate place, with all the canals that the Martians, cut through the globe so they could feed water from the ice caps, to where they were living. So it's kind of nice to see that there's a kilometer of ice there, and it's hundreds of kilometers. It actually grows from 3,000 or 4,000 kilometers across during the winter, during the North Polar winter on Mars, and then it shrinks back, which I'll show in the next image. But it's really kind of nice that they can see this, that they have radar that can penetrate into this. And the only thing that surprised me was that, amateurs can see this. You don't need to have the Hubble. This is images from the Hubble Space Telescope, but amateurs can actually see the seasonal changes in the polar ice cap of Mars. And what I asked the Science Olympiads was, I said, well, what's going on? What really is happening to this image before? What's happening when it shrinks and expands? And the answer was that the carbon dioxide that is right on the very outer surface, instead of being 1,000 meters thick, it's between 0.5, between 20 and 40 inches, between a half a meter and 1 meter thick is the carbon dioxide. And that is covering all of this dust and water ice. So as the seasons change, with the year on Mars about 650, 680 days, a Martian year. As we see this with Hubble, or you see it through your amateur telescope, these changing ice cap, all that's happening is that this white is really the the dry ice, the carbon dioxide, and it is evaporating, or technically it's sublimating, and that's what's happening during the seasons. All of the water ice below it, those 999 meters of water ice, it just sits there all the time. And it's still there, it's just that it doesn't reflect light. So we think, the frost goes away, the dry ice goes away, and the water ice just sits there all the time, because that's the, what would you say, that is the climate of Mars today, okay? They claim that kilometer of water ice built up over millions of years, okay? But the climate of Mars is not such now that there's any, I would say, mobility of that water ice. It's all just this thin layer of dry ice on the top, and that's what we're seeing changing.
Water ice is mainly at both poles, is that it?
They say that most of the water ice is at the North Pole, and at the South Pole you do have the seasonal change, but there, very little water, mostly just this frost, this dry ice that's moving around as it becomes summer at the South Pole. That dry ice gets up into the atmosphere. It works its way it worked by these winds. There's high winds on Mars, and it works its way, and it what's the reverse of sublimating? Deposition. Okay. It deposits on the North Pole, and it just moves from pole to pole, from season, as you go from one season to the other. Okay.
For those who might not know, could you explain what dry ice is?
So carbon dioxide is a gas, and at about minus 110 Fahrenheit, it goes through a phase transition, and because of the phase diagram, there is no transition at atmospheric pressure from gas to liquid. So it just goes directly from gas into a solid phase. And Dr. Hanna here is saying that process is deposition. And then it goes through the reverse when you warm it up above minus 110 Fahrenheit. And the only time you would see liquid carbon dioxide is if you went where we have the atmospheric pressure on Earth is approximately 1 atmosphere. If you go to, I don't know whether I think it's about 100 atmospheres, so about at least 1,000 psig. And then you would actually move on your phase diagram to a point where you would actually see a transition from solid to liquid to vapor, okay? But at our atmospheric conditions, 1 atmosphere, or certainly Mars's atmosphere is 1/100th of our atmosphere, okay? So under those conditions, you don't, neither on Earth nor on Mars, do you see this. And so you can go to Dillon's and you can open up the freezer there and you can pull out a block of this white stuff, this dry ice, okay? And this common name of dry ice is because when it does warm up, instead of it getting wet, it just turns into vapor. Okay, it just sublimates. All right, so that is that story. And then they went on, and they had a lot to talk about ice for the Science Olympiad, so I learned a lot more about extraterrestrial ice, and so they moved out to the icy moons around Jupiter and Saturn. So you have Europa, is one of the Galilean moons, one of the large moons that were observed back 402 years ago by Galileo. So one of his moons, they observed that the surface looks like a crackled surface. It has all these cracks in it, no craters. Like if you're looking at the moon, what would you expect to see if you're looking at our moon? Our moon is covered with craters because it's been exposed. It's this rocky mass that's been impacted for billions of years. In contrast, this Galilean moon of Jupiter, Europa, it doesn't have any craters. It has this whitish surface, there's all these cracks in it, and they found that there's some features here and here. One was called Theora macular, and the other was called Thrace macular, and they believe that the Europa, because it's kind of cold out by Jupiter, is a it's a water world, smaller than our moon. It's a water world. It has an ocean that's probably 100 kilometers deep, and on the surface is what they see when they fly by it with their. This is Jupiter, so this is actually the Galileo mission, and they took these images, but they decided that these reddish brownish features are because there's so much tidal bending of this moon, because Jupiter is such a massive planet. This giant gas world is bending the moons that are going around it in such a way, tidally deflecting it, so that the interior is liquid water. And even though they estimate the ice to be very thick, tens of kilometers thick, they say where these brownish features are, they say, oh, that may be a weak spot in the surface. Like we have, where we have volcanoes on Earth, they got these brownish features, and they say kind of like a slushy area at one time. And so it's not just a frozen world, and so that makes them interested in it. They went further, and they went out to Saturn with the Cassini mission. Also in the 2005 time frame, 2000, and with the Cassini mission, they looked at the rings, they looked at Saturn, but they also looked at the moon Enceladus. And as they're going by, they're watching these geysers shooting up from this moon of Saturn, Enceladus. And they, if you fly over the Earth and you look for geysers, you have to be going over Old Faithful just at the right time to see it, right? It doesn't happen all the time. So they studied this Enceladus. They have all these geysers coming up from the interior. They decide that it's much thinner. Instead of the ice sheet covering this moon being tens of kilometers thick, they think this is much thinner, and they see all these groove features where this Enceladus, again under the influence of this giant planet Saturn, is being distorted. Kind of like the what is that? The ocean spreading, where you have this ring of fire going around the Earth, where the plates are pulling apart, and so you have molten rock coming up from the mantle. In a similar way, you have these cracks. They call them actually tiger stripes, because they cover this moon of Saturn all over. They're just completely covering it, and they associate these geysers with these cracks. To just give you an idea how nippy it is out there, it's at 170 Kelvin or minus 154 Fahrenheit. So as these geysers go up, they immediately freeze. The water ice that's coming up is freezing. Okay, but they do say it's water ice that they see out there. Okay, so lots of water out there. And if you wanted a comparison between these moons and the Earth, where they say that there's many kilometers, an ocean 100 kilometers deep on Europa, probably something similar on Enceladus. The average depth of our oceans are 2.5 miles, or about 4 kilometers. Then, okay. So, we don't really have oceans deep like the oceans on these icy moons. Okay, just kind of we think of our world as being water being very available, unless you're out here in the Midwest in Kansas, or out in the southwest of this country. But relatively speaking, when you think of the thickness of the Earth down to the center, is 4,000 miles, right? So our oceans represent a very thin layer compared to all that rock underneath. All right. Okay. So here we go. Okay, so that was the ice. I missed something, right? I missed something. I missed one other thought was when they started thinking about why they spending all these hundreds of millions or even $1 billion on these missions, they said, well, why are we going out there? And the answer was not because they just had a big budget, but the answer was that they said, well, we're really interested in finding where there are places that could be habitable. Okay, not that we're sending colonists, not that we're sending, that's part of when you graduate from Kansas Wesleyan, they give you a ticket to Europa. They're interested because they're scientists. They want to learn about what it takes to have an environment that you can live in, that you can survive in. And so the habitable zone ended up being Venus, Earth, and Mars. And we're on maybe a little bit towards the inside the middle of that range of distances from our sun. And these worlds out by Jupiter and Saturn, they're nothing like that. They're far outside the habitable zone, but by creating this system where you have these giant planets tidally compressing and warping these moons, you're able to, in a very hostile environment, at minus 170 Kelvin, you're able to warm up the interior enough so you can have liquid water below the surface. Okay, and then they go down to the bottom of the ocean, where it's 4 degrees Celsius, and they find these communities that are not communicating with the surface, and they seem to be, somehow separate from, what's going on the surface of the Earth. So this field is called astrobiology. They say, well, maybe there's some analogy between these unusual environments, the bottom of the ocean, and what's going on these icy moons of the giant planets. And they also say when they do this oil drilling, people love to do oil drilling, they find bacteria living, a kilometer below the surface of the Earth. And so they say in a similar way, you're not linked to the surface, and yet you are alive. And so this is one of the reasons why they're interested in looking at these places and not just looking at the surface. Not just looking at a place that's a kind of a sister planet to the Earth. Okay, that they can imagine other conditions that could be habitable is the word. Not inhabited, but habitable. Okay. Okay, so now I have something completely different, the Milky Way. And this image would look better with the light off. Yeah, it looks a little bit better now, right? The Milky Way here's the Milky Way, okay? So when you look in the night sky, you see these dark lanes, you see these in some bright areas, and it's a big concentration of stars, but a lot of dark stuff also. And so what the astronomers, astrophysicists did, they said, well, let's get other kinds of telescopes. We need other telescopes other than optical. So they got X-ray telescopes, and they got infrared telescopes, and they got radio telescopes. So look at the 21 centimeter emissions. This is all the same picture. This is all the same field of view. Gamma ray, right? So it seems like there's a lot going on in the middle there. And this is a great expansion in our ability to know what's happening in our Milky Way, because what happens with this optical is that dust and molecular clouds, they block the light, and we can't really see the interior of our own galaxy. And so by looking at these different wavelengths of light, the longer wavelengths, like the infrared, is longer than visible. and the radio is much longer. The radio, and so they're able to that's able to actually pass right through the dust. Okay, and so they can see what they couldn't see before the last 30, 40 years. The X-ray and the gamma, especially the X-ray, they couldn't use it too well because our atmosphere blocked all of the X-rays that are coming from outer space. So again, by using space telescopes, they were able to loft them up above the atmosphere that was blocking the light, and they were able to look at our galaxy in its X-ray emissions. Okay, and again, I don't know how many PhDs were generated out of this study of our galaxy, but I'm sure it's many hundreds of PhDs were earned by studying our galaxy. And then,
excuse me, those images of the Milky Way as they would appear in the sky, as it would appear in the sky if we could see in those wavelengths?
yes. If your eyes could see in the X-ray or sensitive in the gamma ray, that's what the sky would look like. And being so close relative to everything else in the universe, it would really stand out, that gamma ray version. Okay, you can see a correspondence between this gamma ray source and this X-ray. Okay, and even the radio. And here's another. The University of Mass, they have a team that takes this data. This is the 2-micron infrared, and they show the bulge, and then they show some clouds and dust that are emitting radio. They're being excited enough so they emit radio. You warm something up and it emits radio waves above, the temperature may be 5 or 10 Kelvin. You warm it up to 20 or 40 Kelvin, and it starts to emit radio. And when down here, they look very close, but this is actually the large Magellantic and the small Magellantic clouds. Now they are this whole Milky Way. They say it's about 100,000 light years from edge to edge. And they are like 160 and 200, 110 and 160,000. So they are not in the same plane. They're on the other side of this wall. They're kind of like that's how we see them, but they really are further away from the center than what you see there. And in order to understand our Milky Way, they compare it with other galaxies. So they look at the nearest sister galaxy to ours, which Mr. Whitthorne has a model of, right? That's Andromeda. That's M31, and they're showing you now an infrared, visible, and other different wavelengths. And so again, here's your visible, what we see with our little telescopes, or what they see with these huge telescopes in the visible. And Jeff has a model. Now the model is, what is the model? The model is, the size of that is 240,000 light years. The 240,000 light years. And if you convert that into kiloparsecs, it's 240. Oh, I see, kiloparsecs. That's M31. And our galaxy, the Milky Way, is kilolight years, and ours is about 100,000. So 100,000 light years. parsecs, it's about 40, maybe 120. Make that 120. Make this like 40 kiloparsecs, and this is about 67, they say. So maybe we make this 200. A lot of parsecs. Okay. The thickness is remarkable. The thickness of our galaxy, they say, is like the thin disk is 0.6 kiloparsecs. Why? That's worthless. 0.6 kiloparsecs with an exclamation. And this is about the same. I'll say 1 kiloparsec. So if I make a kiloparsec, right? Everyone here knows that a kiloparsec is 1,000 parsecs, right? Kilo, yes?
Yeah.
And 3.26 light years is equal to 1 parsec. Okay? So when I read that the thickness of the thin disk on our Milky Way is 0.6 kiloparsecs, I got out my phone cord and I said, well, I'll make a model of this. I'll make it 1 centimeter is equal to 1 kiloparsec. Okay? So 1 centimeter is like 0.4 inches. So times 0.6, I got like 0.24 inches for my model. And again, it's the Milky Way is 40 kiloparsecs in diameter, so that's 40 centimeters, right? So here's 16 inches, 40 centimeters, and there's the thin disk of our Milky Way. So this is the scale. There it is. Now there is some other stuff they call a thick disk, which is old stars, not too many, but the spiral arms are all in this quarter-inch thickness here, okay? And because Andromeda is bigger, right? You can read 67 versus 67. It started out so dark. 67 kiloparsecs. So Jeff is holding up his 67, and its distance, it's actually 770 kiloparsecs away, so 23 feet away. So there you have us, Andromeda, and there you have the here's this Milky Way, and that's Andromeda. Okay, and and the number of stars, we have like 300 or 400 billion stars. Our sun is 1, right? So we have 3 or 4 times 10 to the 9th billion stars. Is that right? 300 or 400. 300 or 400 times 10 to the 9th. And M31, our sister galaxy, has 1 times 10 to the 12th, a trillion. Okay? So you see, here's the Milky Way there. So now can anyone tell me which one is more massive? Here's our Milky Way, there's Andromeda. Has twice as many stars, a trillion versus, or maybe almost 3 times as many stars. So which one's more massive? What?
The Milky Way.
Yes. Why? Dark matter.
Oh. So wait a minute, are you saying that Andromeda doesn't have as much dark matter as Milky Way does?
That's what I'm saying?
Really?
Yes.
How do they know that?
I don't know. I can tell you that I do know. They know it because of the next slide, right? They know it because of the next slide. So it's kind of nice that we don't have to travel for millions of years to look at the appearance of our Milky Way. We can just look at Andromeda and see the appearance. Because in order to get this view of our Milky Way, you'd have to travel out at the speed of light, like like for a million years to get this point of view. Because Andromeda is the 770 kiloparsecs, or 2.4 million light years away. So if we called up the Andromedes, or whatever they're called over there, and asked them to send us a picture, they could zip it along. It would take 2.4 million years to get here, but they could send us a picture, like we have a picture of their place. We could trade pictures, like, what's that? Trading baseball cards. So here's our Milky Way. Now, I just said, this came from Andromeda, right? It shows kiloparsecs, the center, the barred center, the bulge there in the middle is about 10 or 8 kiloparsecs across. It's about 20 down, 20 up, 20 left and right, so about 40. Here's our sun up here, okay? Our sun, there's our sun up there. You can stand, it could be anywhere. And our sun is going around. Our sun is not it's not even in an arm. It's in what they call the Orion spur, this little thing over here. That little thing there is between this arm, this Perseus arm, and the Sagittarius arm. And so we're like in a little spur, and then all of these targets, the circles, they're all different bright stars that are being picked up by this infrared telescope. And we're going around, right? So I guess we're going this way, going around that way. And the distance from the center to here is 8 kiloparsecs. So 8 is 8 centimeters from the center of the disk here. So that's 8 centimeters is a little over 3 inches from the center. And there's a density wave. So you have the spiral arms, they're moving around. So we're going around, we're 8 kiloparsecs from the center. It's taking us like 250 million years to go around. Okay? And what else do we know about this? Oh, and the density wave that's generating the spiral arms, it's generating all of these very bright stars that are being, luminosity 10 to the 4th, 10 to the 5th, 10 to the 6th times the luminosity of our sun. So anywhere from 10,000 to 100 to 1,000,000 times brighter than our sun. All these bright things are sitting in the arms, and that is because you have dust and gas. You have dust and gas in this. Remember, this 1/4 inch thick. This is all happening all inside this 1/4 of an inch of thickness. So you have the dust and the gas, and you have this density wave that's moving through, not as fast as we're going around. So we're going around like a carousel. I don't know anyone here besides, Dr. Hansen, Dr. Hanna may have ridden carousels. They're not too popular these days, right? But you've seen them in movies, right? You've seen these action or thriller movies where people they're running around on the carousel, and the carousel's turning at the same time. Okay, so the horses are going around, but people are actually walking along the carousel, right? So that's what is happening. Our sun is going around. Takes it like 250 billion, 240 million years to go around the galaxy. The density wave is moving slower, so the sun actually overtakes these spiral arms as it goes around. Again, it must be going this way. As it goes around, these arms are being recreated by this, what's called a density wave. So there's a way that you're pressurizing the gas and dust. And as you pressurize the gas and dust by this density wave, you make stars, okay? You start this condensation to form the stars. And the last thing about this that I could say is that the way they generate this image, hard to believe they could generate an image like that, the way they generate it is we look out from our sun and we see in each one of these arms, as we look at these lines of sight, we catch the stars in this place, and out here. So for one line of sight, they see these different arms. In each arm, they see the velocity of the stars in those arms, and so that's how they can establish where they are, as to which arm they're in. And so it's a pretty good trick to be sitting in this thin, somewhere buried inside this quarter-inch thick disc, and be able to look out and be able to see all these features. So that's what these scientists can do. And I'm impressed. But okay. So now we can do this thing with Steve. I have this other image. This, again, they're taking all this data and they're doing animation. So they're showing you, look how thin it is as it spins around, and then they give you all these choices. But if I just navigate, so now they're showing it rotating. That is one revolution every 240 million years, right? And I can rotate it. So there's the thin disk, and you see in the middle there is that clump they call the bulge. And you can zoom in. Oh, and all these little dots out here, all these guys out here, these are all the globular clusters. These 150, 60 globular clusters that are orbiting around. They're not going. They're showing them going around with the disk, but I've read that they don't go around exactly with the disk. And then you can see the spiral arm animation. Let's see, so here they're showing the arms. And you see it says PlanetQuest Jet Propulsion Laboratory, NASA. So here's our sun. Here's these different arms. This is that Orion spur, local spur. And then back. And then, what else do I really like? The halo. Oh, I didn't talk about the halo. So here's the halo. Halo. The disk is surrounded by spherical halo of old stars and globular clusters shown in red. So the globular clusters are sitting in here. I can see them because I'm closer than you. But there's this huge thing that's bigger than the 40 kiloparsecs that were embedded in. And this is still not the dark matter. And then, what else does this thing show? The central bulge, maybe we'll take a quick look at the central bulge. How big? Let's see how big it is.
Well, Jeffrey, if you had a feel for the distance and the velocity of the stars in these different arms, couldn't you get an idea of the density in the center?
They do get an idea of the density in the center. The density in the center is actually a supermassive black hole in the center. But you can see now that this says 10,000 light years, which would be like 3 kiloparsecs, but that's including the bulge. Okay, that's not the thin disk. Okay, so I really thought this was kind of neat to go to this PlanetQuest at the NASA website. You might like to try doing that. Okay, so that's my story about that. But it's much easier to show this animation than it is to build that model. Adding all these globular clusters sticking up, in the air. I thought that this was kind of a nice presentation. And then I also have. Let's see, is it here? No, I wanted to show you what Dr. Hansen just asked. He said, here we go. So this is this. So here is the center of our galaxy. So you saw all those images, the X-rays and and here's the center. And these are stars that are orbiting around. And as they come to this dark spot right there, they make a sharp turn. And so this is worked out to be a black hole, the center of our galaxy, that is 3 million times the mass of our sun. Okay? So stars can be the same size as our sun. They can be 5 times as massive. If they're 10 times as massive, they very rapidly, instead of lasting for billions of years, they last for like 5 or 10 million years, and they go and become type 2 supernovas. But so things that are 10 times or 15 times the mass of our sun. But here you have 3 million times the mass of our sun. Nothing's there. There's no bright star there. And all of these stars, they're recording this. The gal, this Andrea Ghez, is a postdoc working at UC, I think this is, yes, UCLA. And she is looking with infrared. Infrared is how they can see the center. They can actually see those stars moving around. And this is not, Andrea, and this is not that's not, yes, it's an animation, but it is real data. That they are showing you not a artistic rendition. That's in their technical paper, that movie, or this movie.
Now,
all these stars.
those stars moving?
Very fast, as well, just by Kepler's second law. When they get really close to that black hole, they're really zipping along.
So they're moving fast enough that you can see their motion in real time?
This is over months, okay, but not
Just
over
months?
maybe 2 years.
That's still
But
incredibly
it's
fast.
incredibly fast. Yes. I think somewhere in the technical paper it said it's based on data that goes back 10 years. Okay. So some of the slower things are.
But those must be traveling an appreciable fraction of the speed.
Yeah, they might be going 10% of the speed of light. But it's nice to do that rather than to fall into that black hole. I mean, if you're a star, you'd rather not go to that black hole. All right. Let's see what's next. Oh, so this is. But this is not a, people look at this and they say, oh, that's all made up. It's not made up. This is what these scientists do, okay? So, that's the super show. Oh, and I picked up on this because I watched a NOVA program titled Monster, what is it, Monster, something about a monster. There's a monster. The monster. So you really should watch it. You should really, Monster of the Milky Way. So that was the monster of the Milky Way, okay? Supermassive black hole, monster of the Milky Way. Okay. Now, did that. So when you were watching that, saying something about Kepler's law. So of course I wanted to see what was that law. That was that P. That was that P. That period squared is proportional to the semi-major axis. So you have this. Yeah. So I think that supermassive black hole is something they've been studying just the last few years, and so you have this this period. I can't find one that works. I got something here. This was the last one I used. So you have that equation, that Kepler's third law. Yes, it's a third law. Yes, period squared is equal to a to the third, where this is the semi-major axis of an ellipse. So here's the sun at one of the foci. Here's a planet moving around, and the semi-major axis, I think, is this distance. This is a here. Am I right? Yes. Okay. So just to show how good Kepler was, he comes up with this nice formula that the period is equal to, in the units here is astronomical units, where Earth is 1 unit away, and the period was in years, or Earth years. So years and astronomical units. And so you can see that if you square, I use in Excel, I use a caret symbol to represent the square. So this here is just taking this period, 0.24 squared is 0.06, or maybe, let's see, here, Saturn its period is 29 and a half years, so 30 squared is 900. So this is p squared, and here's the semi-major axis. Again, here's Saturn, 9.5, and so if you cube 10 times 10 times 10, you get 1,000. But you can see how close they are. That this formula worked out, like in 1620 by Kepler, this genius of a mathematician and astronomer. Mostly he was an astrologist, though, because that's what you got paid to do astrology. But he worked out this relationship, and then Newton came along, 70 years later, and he showed how you could justify this by his general law of gravity. Okay, so I thought this was nice to see this relationship and how well it works. This very close. If you ever did experiment, this model of Kepler's here, the period squared is equal to the semi-major axis cubed. If you ever got experimental data that was this close, they would question your academic honesty. But that's how good celestial mechanics are. That they work so well. They follow this model so well.
It was so amazing that he come up with that without even knowing the astronomical unit.
He didn't know how far it was, but he knew that just like I did a model here, he did a model of our solar system where everything was scaled, where his yardstick was 1 astronomical unit. Okay, and he said that Saturn was, 9.55 times further from the sun than the Earth is. Okay, and he built this model, and it followed his laws. They move in ellipses. They sweep out equal, that angular momentum thing. The second law, they sweep out equal areas in equal time, which is really a conservation of angular momentum. The second law, but why I show this is because of the next slide. So here we are again. We're moving around once every quarter of a billion years. We're going around, and if we were following Kepler's law, of course we would, as we went further away from the sun, or the center of our galaxy, we would go down this curve. Our velocities would go down. So sure enough, they look around at these other open clusters and other things, those bright objects. They measure their velocities, as I was saying before, looking through the plane, and then sure enough, they find that no, we don't follow Kepler's law. We don't follow Kepler's third law. You can take the period, and of course, as people know, you can take the period, and what is the period? But is the distance. What? You have the distance times the velocity is equal to the period, and the distance is really like 2 pi a times the velocity is equal to the period. Okay. Because a, if you were thinking of a circle, a would just be the radius. Okay, so 2 pi r is the circumference times the velocity would be the period. Okay, going around a circular track, yes, and you would, if you're going at 200 miles an hour around a track that was 10 miles long, it would take you a 20th of an hour, right, to go around. It would take you 3 minutes. Yes, same idea. Okay, so we don't do that. The reason why we don't do that is because of the dark matter. So they looked at this problem, and they said the mass is not like our solar system. 99% of the mass of our solar system is concentrated in the sun, okay, and all these little planets that go around, even the giant planets are tiny compared to the sun. And in contrast, this halo and dark matter that surround our galaxy, all that extra mass that's around allows all of the stars to zip around in the thin disk and more or less go at about the same speed. They go about 200 to 240 kilometers a second, okay? So everything is going around at about the same speed. So the guys that are in the inside, they get around faster than the ones on the outside. Okay? And so that's something, again, that pointed them towards this idea that there has to be some dark matter going and allowing all this this fairly uniform motion. And then I'll show just a couple of images. There's a massive star. It's very massive. I said that big stars, very quickly, in a million or a few million years, they become supernovas with 10 or 15 times the mass of our sun. Well, this Eta Carina?
I call it Ada.
Ada, okay. In the southern hemisphere, it's a seclination is minus 59, but apparently, if you're in the Mediterranean, you look down at the southern horizon. Well, this John Herschel, the son of William Herschel, who discovered Uranus, he saw this thing brightening, like 1,000 times brighter. Got to it was the second brightest. It was the second brightest star in the night sky. Sirius is the brightest. This got to minus 0.8. Currently, it's about 4.5. So it is actually visible. If you went down to South America, Australia, you could actually see this thing. And they came up with a theory about how this thing was 100 or 150 times the mass of our sun. It's blasted off like 30 solar masses over the last century or so. So it's very, very exciting what's happening to this thing. The star. Where they have supernovas, they'd say this may turn into a hypernova. Anytime, maybe tonight. And so then they started looking at this. They had very fuzzy images from the ground, and they got this image from Hubble. And this image from Hubble, when they first sent Hubble up in like '89, they got this image of this star as these two lobes. It has this ladder-like feature going that way. It has all these spikes coming out, and they didn't really know what to make of it. They couldn't explain it all, so they waited until the corrective optics were fitted to the telescope, and then they had the GM test. So this image on the right here was the first image they got of this massive star, 100 times the mass of our sun, in late '93 and '94. So the writer of this book, this Robert Zimmerman, The Universe in a Mirror, because the Hubble telescope, our space telescope, is like a big mirror in the sky. This was not part of the presentation of NASA. So NASA has all these reporters come to their conference, to their symposium, and they say, we're not going to show you this. Why? Because it didn't pass the grandmother test. The astronomers explained this to the journalist. They said, if they showed this, everyone would say, my grandmother can't believe that that's in outer space. Okay, it's impossible for this thing with all this luminous red hydrogen being excited by all the energy coming out of this explosion that happened probably at least one of them happened in the 1840s. And so, but that's what, and the ladder went away because the ladder was an artifact of them trying to decipher from that unfocused image in 1990 when they first sent up Hubble with the defective mirror. That ladder went away, and there are jets coming out of this thing. This, I guess, is a jet. There's some kind of a disk over here. And this is just a later image with maybe a little bit better camera, 96. Same object. It just flipped over. That's why this lobe is, that, whatever. But this is the same star. There's the center of the star. And then more? This is one more. So they're superimposing it. They love to superimpose from one telescope to another. So they have another space telescope that measures the X-rays. As I said, the X-rays can't be measured on the Earth. They have to be above the atmosphere. And here they even show the size of it. It's like 0.8 arc minutes, the angular size of this thing. So you have both the Hubble image and you have all the X-ray light that's all being generated by this a very energetic star. And I thought that was kind of a neat example of what you can do with instruments. You can make them better, especially if initially they're bad. And the last thing with this Hubble, this is an image of this supernova that they've been waiting for centuries for. So the last supernova was observed by Kepler, maybe in 1604, and they were waiting since then with all their modern telescopes in the 19th century, the 17th century, the 20th century, and finally, in 1987, you had this supernova. And again, this is a Hubble image, and it has all this amazing detail of expanding gases and generating all the heavy elements as it expands. So I thought that was a kind of a neat image. I think I'll stop as I've run much longer than I had planned to. Are there? I did have. What was it? I did have the dawn. I'll just show the dawn. I'll stop there. I'll leave the variable star next time. So this is again. They're looking back in time. As they look back in time, of course, they can see galaxies forming, merging, what they call a cosmic dawn right after the Big Bang, maybe like this is like 500 or 400 million years after the Big Bang, and they claim there's three galaxies that are coming together. This, and all of this stuff here is ionized hydrogen, I think I read. And they said, well, it's interesting because it's all primordial. They say where we have lots of, heavy elements here, they say this is just hydrogen. That this is really what they call a primordial galaxy. That it's before stars have started to synthesize all of the heavier elements. Okay. So that's what they do, and maybe next time I could talk about world picture versus world map, or maybe someone next time could tell me what that is, the difference between the world picture and the world map. But that is to give you a hint, that's a world picture. Okay, so thank you. Hope you learned at least that something exciting is happening in astronomy today. And questions? No questions? Good. Okay.
Well, I have a couple questions.
You have a couple questions. Okay.
Those Hubble images, are those color enhanced? Are those visible light?
What they're doing is they have these color wheels. So you have filters, and Hubble can actually read into the infrared. Okay, and so when you see that image here, some of this would be visible and some of it would be infrared, and so they distinguish between those different layers, similar to when you construct a color image, you put layers of from your yellow, your blue, your red filters, and you combine them to make a color image from black and white. So I think it's not. Some would say when you see the X-rays and the gamma rays, obviously there is no corresponding color. But this is, you could say that this is the way that the scientists can interpret this data is by showing different layers of data with different colors. Okay.
Which are basically you're seeing visible and infrared.
You're seeing in this case, I think you're seeing visible and infrared. In other ones, they put another layer of X-rays on top, like I showed you for that massive star. Okay, that they're layering, and it really is our years to reveal. I guess it's the same as like the GIS. They have all these layers of information, mind can integrate, and the scientists can integrate that information and be able to see the interaction between like what generates the X-rays, what generates the infrared. They can say, oh yes, there's a relationship. This is almost like the quasars, when the quasi-stellar radio sources. They didn't have any visible light correspondence, but then as they worked on it, they actually were able to show that these were the bulge of very distant galaxies, were both radio sources and visible light sources. And so again, they were able to create that association. And then currently what they're doing is gamma ray bursters. They've done some success with that these things at cosmological distances that are issuing a burst of gamma rays for 5 or 10 seconds. They're learning to associate that with objects that they can see. Okay.
Some other images I've looked at, the gamma rays are the result of like a shock wave that precedes the actual matter or gases, the excited gases.
It might be the neutrinos that are
going
being blasted
up,
out.
maybe, but it's impacting the gas around the star,
Yes.
and you're getting the X-rays given off, so you can kind of see the shock wave.
Yes.
Looking at the X-ray image.
And they talk about a reflection that that there's an echo, a light echo off of the material that's surrounding interesting objects. Okay, so anything else?
But back at the beginning, when you had the image of the Milky Way and there was that bright spot, did they say anything about what that bright spot was?
I didn't read that. Yeah. So you had the multi-disc.
Yeah.
So this one there. I'm sure.
X-ray.
I'm sure that every one of these is, as I said, is a bunch of papers. And since you see both an X-ray and gamma, I'm sure that, and there's one over here too. Then this one down here, that those are definitely.
But they didn't say anything particular about what that was.
No, this is a poster. So, but there's a whole. Every one of these images, there's a page of text associated with almost every image that I showed you tonight, and so you can read, and even these two here, probably these up here, right? So there's a correspondence.
Is that on the NASA website?
Yes, it says NASA. Right. The NASA, being our government, where we have all this copyright stuff with everything else on the internet, this is all free to use, especially for educational purposes. If I was trying to make money doing this, maybe there'd be an issue. But here, in infrared, you have something here, and obviously in the radio, you have something else going on over here, and in this other radio up here, you see that, okay? And so definitely they work to figure out what's generating these strong sources, basically. Okay.
Another interesting question for my students, but not yet in this semester, after we study a little bit more about stars, it's interesting that the atomic hydrogen image, which is the second one from the top, there's more atomic hydrogen as you move away from the center of the galaxy, which might initially seem counterintuitive because, the matter is more concentrated at the core. So why is there more atomic hydrogen for the outer portion of the disk? What's going on there? And don't answer the question for them because that sounds like a good test question at the end of the semester.
Okay, Jeffrey,
Yes.
real quickly,
Yes.
why do I have the Andromeda disk and why do you have the Milky Way disk? What's going to happen?
Oh.
When?
What's happening is that disk is approaching this disk at 300. Oh, they're so close to each other, being only this 770 kiloparsecs away, 23 feet away, that they're being pulled together. So the universe is expanding, but these two galaxies are heading towards a collision. They're merging, and in 3.75 weeks, billions of years, give me that. They're gonna pass through each other because they're basically empty space. So they're gonna pass through each other, but they say they're gonna kind of like do some kind of a dance around each other, and maybe they're gonna merge, maybe not. and maybe the Earth, the sun will be expelled before it becomes a red giant. So maybe that history or the life cycle of our sun, it may not make it to being a red giant in as part of this thin disk.
Well, but that wouldn't affect the evolution of the sun, would it?
Well,
I mean,
if it gets tossed out, so what? And
not so many stars in the sky. Astronomy class would be easier.
right.
Yeah.
Yes. So, but I basically, the space is so infinitely empty. It seems like it won't be a problem.
There are models that you
Yes.
can
Yes.
watch. There are some.
Yes, that twirl around. Simulations are very important because obviously you can't do experiments on the universe. So the idea of modeling, the way they model and predict the weather forecast for tomorrow, is unreliable. So we think, well, the models that the scientists use are very important. I think that this astrophysicist coming from KU, this Steve Hawley, next Thursday, he'll be here at 1:30 for those people who want to actually hear a scientist and astronaut talk. I think that in his research, he does a lot of work with simulations, okay? Because that's a big part of being an astrophysicist, okay? And so that should be exciting if you don't have a conflict, if you can come at 1:30 on Thursday.
Yeah, I haven't had an opportunity to tell my class about that because we just didn't have class this week.
Uh-huh.
But we do have a visiting. Steve Hawley is a Salina native, who was an astronaut, and when he retired from being an active astronaut, he took up a teaching position at the University of Kansas in astronomy, and he's going to be coming and visiting and giving a talk. A little bit about his experiences and also on his research.
And he's an unusual astronaut in that he said that he was really like to be one, but he didn't want to be a fighter pilot or a test pilot, and so he went and got his doctorate. And as a postdoc, he saw on a bulletin board in one of maybe in his department or some other visiting department of astronomy, and they said back in the early 80s, maybe 81, they're looking for more astronauts for the shuttle program, and he looked immediately to see what the minimum requirements were, and there was no mention of being a test pilot, and so he applied, and that's how he ended up getting into that corps of astronauts. So that is just a change from the early program. The Mercury astronauts, they all were military, and they were warriors, basically.
Well, they were pilots. They had pilots.
Fighter pilots. They were not flying cargo
Weren't
planes.
scientists.
Yes, they weren't.
Exclusively.
Yes. Yes. They might have been engineers, but they weren't. They were, and some people thought of them as just being, spam in a can is what they called it in the right stuff. All right. So we have the refreshments.
Jeffrey, do you know what room Steve will be talking in?
Right here.
Is it this room?
Yes. So you don't have to wait online. You don't have to camp out here. I'm sure they'll. And Dr. Welter, she said something about that. If there's a standing room crowd, maybe it'll be moved. Yes. Yep. Okay. Neat.
All right, let's thank Mr. Kessel.
Yes.